Bon, c'est un très grand plaisir d'avoir Klaus avec nous aujourd'hui. Je le présente en français parce qu'il pourrait très bien parler français. Voilà, il comprend le français parfaitement. Donc Klaus travaille à l'Institut Niels Bohr à Copenhague et aussi à l'Université de Copenhague. Klaus, bon, c'est, je crois sans conteste possible, un des grands théoriciens de l'optique quantique au niveau international et aussi de tout ce qui tourne autour des technologies quantiques maintenant. Je dirais qu'il a la grande chance d'avoir une porte nommée à son nom. Ça n'arrive pas à tout le monde. Hein. Alors, quand je dis une porte, je parle d'une porte logique. La porte Mølmer sur Sorensen. Voilà, non, c'est pas un porte-maillot. Hein, voilà, avoir une porte à son nom, c'est quand même quelque chose. Et voilà, donc c'est un travail que... La porte, c'était dans les années 2000, hein, c'est ça, 99-2000, oui. Que vous avez travaillé avec Anders là-dessus. Voilà. Et c'est une porte qui est utilisée pour les ions, pour l'électromicrocavité. Je crois même pour les jonctions supra, il y a quelques implémentations de la porte Mølmer Sorensen. Voilà. Bon, Klaus a fait plein d'autres choses, je ne vais pas les lister toutes ici, mais il a travaillé, alors je vérifie quand même que je n'ai pas oublié trop de choses, sur les atomes de Rydberg. Il a un article de revue en particulier remarquable, mais il a aussi beaucoup de choses, de contributions originales. Il a travaillé sur les mémoires quantiques, il a travaillé sur les états comprimés, ceux dont on a parlé dans ce cours. D'ailleurs, il m'a demandé de ne pas effacer ce qu'il y a au tableau, donc il y aura peut-être des recouvrements en direct. Voilà. Bon, j'oublie pas un bébé qu'on a eu ensemble, aussi avec Yvan, il y a maintenant assez longtemps, c'était dans les années 90, qui était ces trajectoires quantiques qu'on a faites et dont tu vas nous parler aujourd'hui. Ça va faire l'objet de ton séminaire. Bon, je peux dire avant ça un mot de toutes les récompenses qu'il a eues. Enfin, il y en a eu beaucoup, donc je ne vais pas les donner toutes, mais je peux donner les plus récentes. Il y a eu le prix de la Fondation Carlsberg, c'était en 2025. Voilà, Carlsberg, c'est celui qui fait de la bière. Hein, donc, voilà, et c'est un mécène de la science absolument incroyable. On aimerait que les fabricants de bière françaises donnent ne serait-ce que le 10e de ce que donne Carlsberg à la science française, à la science danoise. Il a eu un prix von Humboldt en 2023, la médaille d'Irak de l'Institut australien de physique en 2023 aussi. Klaus est fellow de l'American Physical Society, et puis bon, il y a une longue liste comme ça de récompenses. La dernière chose que je voudrais dire, c'est que, en plus d'être un très grand physicien, Klaus a aussi beaucoup de connexions avec le monde de l'art. Il a composé de la musique en essayant d'apporter des concepts quantiques en musique. Tu me disais hier que tu avais aussi des interactions avec des gens qui font des ballets, avec des artistes peintres ou qui font des installations. Donc ça aussi, c'est quelque chose que j'admire beaucoup chez toi, c'est arriver à transposer des concepts quantiques à un domaine qui n'est pas la physique, mais qui est un domaine plus vaste que ça. Donc voilà. Merci encore d'être venu et puis on est ravis de t'écouter.
Merci beaucoup, Jean. Thank you very much. I can give a talk in French, but I think if I give it in English, I can communicate more of the content of the talk, more easily at least. Before I give my talk, I'd like to say that I was spent time here, an internship with Jean and Claude 37 years ago. It was really the kick-off of my career in the sense that it was really what confirmed that this is a community I wanted to belong to, that this is a job I would like to have, and I have not regretted 1 second in my entire life. I still have the same excitement meeting people that I met over the years, and I think the spirit of the École Normale Supérieure at that time and my French colleagues and communities still today confirm that we have something unique. And so I'm very, very happy and also very grateful to Jean and Claude and the colleagues at that time for actually having taken good care of me, the same way as we all now try to take good care of young students and postdocs coming in our groups, of course. I'll be talking about quantum sensing with quantum trajectories, and as Jean just said, quantum trajectories is something we worked on a long time ago, but it has been a subject that keeps giving in some sense, so I will also give you a mini review of what are actually the old quantum trajectories from the 1990s, but how they fit into the sensing issue. You could also call the talk something else, like how quantum trajectories became the tool of analyzing measurement data. This is the Bohr Institute from the outside. I just want to take you on the inside of the Bohr Institute. This is one of the famous pictures, 1930, a conference at the Bohr Institute. In the first row, you see all the famous physicists You see Niels Bohr, of course, you see Heisenberg, Pauli, and here's Lev Landau, here's Hans Kramers. You also see the trumpet that Heisenberg was using to play a fanfare if he liked the talk. The gun that Pauli, famously a grumpy guy, used to shoot the speaker if he didn't like the talk, and this mechanical monkey that would be agitated if something fun was happening in the talk. Now, these people were, of course, the pioneers of quantum mechanics, and at that time quantum was something that just happened. Quantum is the laws of physics, particularly the laws of the microscopic world, so there are phenomena who are quantum by nature. Atomic physics, molecular physics, solid-state physics, all the things that were emerging. And we talk about the first quantum revolution, the gradual understanding of the consequences of quantum, but also many, many technologies just follow from the properties of atoms and solids and whatnot. Now, in modern times, this is a picture in the same room, and I'm sure you recognize quite a few people in the room. Serge Ross, Alain Aspect here, David Gross, and we have in the back Philippe Granger, just to mention a few of the French colleagues. This was an event sort of celebrating or having a conference on what we today call the second quantum revolution. Maybe a little bit of an inflated claim, but at least there's this claim that now we are doing quantum with a purpose. We are designing quantum properties. This is something that started already with the emergence of quantum optics. We were using lasers to cool atoms, to prepare atoms for some purpose, for example, precision spectroscopy. We were creating trapping potentials to trap ions, so suddenly the center of mass motion would be quantum mechanical, and of course the condensate that Jean was just talking about. So now it was a little bit more engineering using the forces of quantum, but then also having a purpose. And some of this quantum revolution stuff is the applications that many of us are also looking into today. Now I want to draw your attention to this picture in the back of the room, which was always in the back of the room. This is a picture of Ole Rømer, who 350 years ago determined the speed of light. Okay, he was actually here in Paris, and he was using observations by Cassini and his own observations, and he was concluding that there was a finite speed of light, so he actually called it the hesitation of light. Cassini didn't like it because he thought the number was too high. He couldn't imagine anything moving that fast, but it's actually a remarkable thing and also very inspiring in the way you try to learn something from data. So these were the occultations of one of Jupiter's moons, and I don't know if I could have invented, even today, the method that he was actually using. And of course also the very precise analysis of those data. Anyway, let's get into my talk. So quantum technologies, you often hear about the three pillars of quantum technologies: quantum computing, quantum communication, quantum sensing, and I write easier because that's often stated that the quantum sensing part is something we already do. And that's fair to a large extent. There's also a lot of quantum sensors today who are maybe a little bit more first quantum revolution, because the fact that atoms have spectra means that atoms are very good probes of many things, also very important things, and also very high precision probes of something. When we talk about the second quantum revolution, atomic sensors, it's about making entangled states and the collectively squeezed state that Jean was talking about just before this presentation. So there's a new twist where we are still massaging the system a little bit more than what nature gave to us. And I put easy in a bracket. I would say, though, that even though we make many, many claims about quantum sensing, it's very often not these tricks that are used in practice today. It is very often easier to get the good signal to noise by just having more atoms. And having a versatile, running 24/7 sensor, preparing it in very fragile quantum states is not that easy at all. But this is something we are looking gradually into the future. And I mean, just to maybe give a beginning pitch to my talk, in 1947, the first transistor was realized. It's the size of, let's call it a pack of cigarettes inside this glass ball. And now today, of course, we all have a billion of them on a chip the size of a fingernail in our phones. Okay. So when was the transistor first used for anything useful? The integrated circuits belong to the 1970s. So there was actually decades where there was no computer coming out of the transistor, really. Okay. But I'll show you a picture here from early 1950s, 1952, 1953. This lady is holding in her hand the first commercial application of a single transistor. And it's a fantastic application. I feel a little bit moved every time I show this picture and talk about it, because it changed her life. It changed millions of people's life. So I don't know if you have a guess what was the first commercial use of transistors. Hearing aids. So there was radio, it actually only came 2 years later than the hearing aids. The first thing was the hearing aids. So hearing aids, electronic before that time, was of course radio tubes plus 6 kilograms of batteries because they used enormous power. So with this thing, it contains the battery also inside that box. So hearing aids were sold in the millions, first by some, of course, pioneer companies, and then Hewlett-Packard and others actually entered, and millions of people had hearing aids already at 1954, 1955, when the first transistor radio was actually commercialized. So I think this is a good lesson. And of course, it has a little bit to do with the sensing thing, because one man's very little and useless quantum computer could be another person's sensor, like the sensor in the hearing aids. So let's go to the sensing. And just to give a broad introduction or motivation for sensing, there are many, many situations in which we use quantum systems for sensing. So what I show up here, where we use one particular property, this is a diamond with a nitrogen vacancy. So this is a little impurity inside the diamond, which acts like a little spin. And that little spin is, of course, sensitive to magnetic fields. So if you put an interesting molecule on the surface of this diamond, there will be spins in that molecule that will interact with your little sensing spin. And this thing can be interrogated optically. So that means you can actually see the motion dynamics of that spin due to these different components. And by clever protocols related to what we use in MRI scanners, we can actually very selectively both look in different directions and sort out things that are at different distances to that little spin. A kind of mapping out the magnetic environment of that spin is telling us how maybe this protein is folded or what are the atoms in this protein. So that's very exciting. Up here, you see a patient in a hospital, or of course it's just a drawing. Above the chest of that person, you can put little glass cells containing atomic vapor. And then you can shine laser light through these to interrogate the atomic behavior. Okay, so what makes the atoms behave? That's the currents in the heart who give rise to a magnetic field, and the magnetic field gives rise to a Zeeman effect, who gives rise to a distortion of the spectroscopy of these atoms. So in this way, you can map out 3D what are the currents in the heart of a patient, predict or diagnose if there are some anomalies in this person's heart. There are other ways to do that, but these are very sensitive, and the atomic sensors are now winning also in the imaging of the brain, because you can actually put little cells with atomic systems inside all the way down so they touch the skull, and then you can do imaging, while if you use the squid, you have to have an insulating layer because they are very cold, of course. So you actually get further and further away with these sensors. Here you can get much, much closer. Down here you see this is actually a French company or startup out of a big European project. This is a gravimeter, or where you have atoms, cold atoms, laser cooled in lattices. You let them drop, and then you can measure the gravity, but you can also measure, of course, if there are vibrations in the environment. This one is mounted on Mount Vesuvius. So there you can actually monitor for earthquake warnings and stuff like that. And this autonomous system, as I understand, you can put it up, it stays there for half a year, turns on and off by itself. Really remarkable. Why is that interesting? Well, of course, I can give many good reasons, but one particular reason is, if you look around the globe, there's a local dependence of gravity, of course, on what are the minerals and the structure of the earth underneath. So this is actually seen by some as a new way to do navigation. So you can navigate by measuring the local gravity. So that would be navigation for submarines, for example, who don't have the GPS signal at their availability. And this is why you have French and other projects flying over the Atlantic to actually, with this device, map out the gravity so that you can sail and navigate by the variations in gravity. Okay, on the more scientific side, this is Katori in Japan, who is putting his very nice little mobile atomic precision clock, in this Tokyo Tower, and then he can measure how time goes faster at a higher elevation than lower one due to Einstein relativity. And just to give you the state of the art, this is Yunye's experiment at Gila Boulder, where he can measure within 0.5 millimeter height difference time going at different pace due to general relativity. So this is high precision, high sensitivity with some fundamental issues in mind. And what I think is the most remarkable, and to me actually maybe the only real example where quantum effects today is the limit of sensing and where we do quantum tricks to improve it, is the LIGO experiment. So this is 40 kilogram heavy mirrors mounted in the LIGO apparatus, and when gravitational waves pass by, there'll be effectively the equivalent of a motion of these mirrors that you can monitor because they form part of a big interferometer. And the sensitivity of that interferometer is remarkable because the motion is the size of a proton. Right? So it's just insane, and it's actually the same as the ground state width of that pendulum. So therefore, you are at the quantum limit of the motion of that mirror, or at least the detection of the motion of that mirror when you're doing this kind of probing. So these are all challenges where you push the limit using quantum systems, and where there's a prospect to go even further by playing quantum tricks like the squeeze state that Jean talked about. Now, so how does quantum sensing work? Okay, so in this talk, I'm not going to say, wow, now we'll understand one sensing scheme at depth. I would rather like to give a talk where I discuss some of the principles of sensing, in particular the kind of sensing I'm interested in, namely continuous monitoring of a system. At LIGO, they are not preparing the LIGO, expecting the gravitational wave to come, and then they measure after the wave. They're, of course, looking all the time because they don't know when these waves are coming. So they have a special situation in terms of sensing that I'll talk about. But generally, the idea is that the quantum system is subject to some perturbation, a field, a force, an acceleration. This perturbation will change the state of the system. It will be part of the Hamiltonian, so the Schrödinger equation will contain a term that depends on this V term. And then, of course, it will also change, therefore, the probability distribution for the measurement outcomes. This is quantum mechanics, so it's not enough that you change the state. You also have to say what consequences does it have for measurements, because we have to measure the system. So we're going to have folding in Bohr's rule and randomness of measurements if we want to analyze quantum sensing. So the analysis is sort of an easy way here. You establish in many experiments just a proportionality between the V and the measurement data. Maybe a magnetic field shifts a spectrum by a certain amount due to the Zeeman effect. You do spectroscopy, you plot the spectrum, and you see what is the shift. That's telling you what is the magnetic field. But maybe there's more information in the data record as it accumulates with time. And I'll show you a few examples of that. So this proportionality between an average signal or an integrated signal with what you're interested in is certainly true, and a relatively simple analysis, you may even calibrate it on the fly, but there may be more information, of course, in the details of your measurement record. If you just do this proportionality, you might say that then the error in the estimate will depend on how much the data depend on the perturbation. So there's a derivative here, and then there's a statistical uncertainty of the data, which is, of course, part of your data record assessment. So where's the quantum in this story? And the quantum, just to answer it immediately, is, of course, that these are quantum measurements that obey a Bohr rule and are governed by the quantum mechanical rules of measurement. So there could be quantum limits to this signal. And actually, Jean already mentioned that when he has the squeeze states in phase or a number, you are more sensitive to changes in those numbers. And that's, of course, because even a small change is visible if the uncertainty of the variable you're measuring is small. So that is the whole idea of squeezing, and what Alice certainly also talked about in her now 3 years ago presentation on squeeze state. So there are limits set by Bohr's rule and the randomness of outcomes. There might also be limits set by the Heisenberg uncertainty relation, because even though Heisenberg doesn't give a limit on one observable, but only the product of two, when you measure one, you may affect the other one and cause that to become more uncertain. And maybe that other degree of freedom is part of the evolution of the system. If I measure the position of a particle, the momentum becomes uncertain. But that means the position later will have picked up uncertainty due to that. And Schrödinger actually made a Heisenberg uncertainty relation for position at 2 different times, which is exactly due to this effect. So the LIGO is challenged by wanting to measure position very precisely all the time, because the momentum uncertainty coming from the measurement hits back in the experiment on later measurements on LIGO. So there's a lot of very exciting things here to talk about, and I'm gloss over it because then I'll get to what I prefer to talk about. So there's this idea that you can prepare an initial state, evolve and measure, and then you will have an interesting discussion. And there are the issue that you can have many, many good ideas to employ squeezing, entanglement, and whatnot. And I'm going to talk not much about that, because this is true, but my focus will be on how do we analyze the best a given sensor's operation. So you may come with a good idea, say, I want to use the squeeze state. And I say, thank you very much, let's use the squeeze state. Now I will help analyze what the data tells us when we're doing the measurement with the squeeze state. Or I will use a mechanism by which I get particularly sensitive, and I'm going to say, great, you're smarter than me at coming up with such ideas, but maybe I can offer a tool here to how to best analyze the data. So that's going to be the theme of this talk, actually. How do we analyze the data that are coming out. And they'll refer to two very nice papers here. They're already 20 years old, but talking about quantum-enhanced measurements and what you can do in this whole area. So there's two kinds of things you might like to test, and I like to present both, maybe mostly because what I call hypothesis testing is a good example of what you like to do. So here is a system prepared in some funny initial state. This is actually the Husimi function of an experiment in Heidelberg by Markus Oberthaler. So it follows exactly this notation by Jean, so I asked him, please don't remove this blackboard, because this could also look like that. That's a very funny state, but that state is maybe thought to be particularly sensitive. And if you apply some interaction on it, and I think in Markus' case it's an interaction a bit like this one, then it transforms into a modified state. So this is your wave function who has evolved with time. And now, of course, the new state depends on how strong was the perturbation. Were you exposed to Hamiltonian H0 or H1, or were you supposed to an evolution due to a parameter theta or a slightly different value of that theta? And what I write here is the state overlap between those two outcome states, because that's actually formally what sets the limit for my ability to distinguish. Did I get that state or that state? And I can see the difference between two states if they are orthogonal, without any error. But if they're not orthogonal, then there will be an error in that discrimination, which exactly depends on the overlap between those two states. So the overlap is, literally speaking, my ability to distinguish two hypotheses, or also two nearby hypotheses, and thereby the precision of a measurement. What is the best measurement strategy? Well, if you have only two states to distinguish, it's actually, you can think about them as two vectors in a plane, and you just have to find what is the operator who has the highest discrimination towards these two. So that's actually a well-known problem in quantum mechanics. And if you want to estimate also the mean error, or the probability that you give a wrong answer here, that's also given entirely by that overlap. And I'll come back to that. So let me just see, how do we get about doing the measurement? But because it's not sure that I can actually distinguish those two quantum states, that measurement might be completely crazy. Maybe I can measure the z coordinate, what Jean called the dz, and the dz coordinate is quantized, it has discrete integer values, and I'll do projective measurements into these eigenstates. So that means that if I take that state, I can get any value of jz which is within this distribution. And if I do many measurements, I will get a histogram. And that histogram is going to be random, because there's going to be statistics involved with how many times do I get m equal to 0, m equal to 1, m equal to minus 1, as we saw in Jean's presentation. So here's an example of what such a histogram could look like. So this is what I would call the measured data here. And if I want to know if that measured data is in agreement with, say, one state evolved during one Hamiltonian or another one, then I have to compare that histogram with those two, the predictions based on such two model Hamiltonians. And I have to infer, if I can, what is the error probability or what is the error bar associated with this assignment. So let's just assume a simpler case first. I'm going to toss a coin, and I'm going to find out if it's a fair coin or an unfair coin. So let's call 0 heads and 1 tails, and then I get a number of zeros and a number of ones. And of course you would say, okay, the probability of getting the ones is just the number of ones divided by the total number. So that is the parameter theta, the unknown theta parameter for this particular coin. But you have to remember, I've just tossed this coin maybe 50 times or 60 times. If I do it again, I'll not get exactly the same values. There's going to be an error bar, which is here given by the binomial distribution. So I even know what is the variance given in this experiment here. So this error bar on those two numbers, of course, translate into an error bar on what is the balance of the coin. So this is how this simple example shows how data and their fluctuations translate into an error bar on the quantity we want to estimate. So the same is true for the much more complicated situation up there, where this is my data set, and maybe there's a prediction for one value of the parameter that is the red curve. I was just drawing all of this by hand, so don't interpret this as very important physics. And maybe another parameter suggests this distribution. Which one looks the most like the blue one? And in any given case, there will actually be a way to do that. And I'll do that in an even slightly more complicated situation on the following slide. But I will introduce to you a quantifier for how good is the estimate going to be. So when I talked about the coin, I knew there was a binomial distribution. I knew what's the probability distribution for the different kinds of data I would get. And I know how much that would depend on the parameter theta. And from that, I could estimate what's the error bar. And a similar thing exists in a much more general case, and it's called the Fisher information. So there is a quantity, which is the uncertainty, which can be written as 1 over the square root of the Fisher information. This is called the Krammer-Rao bound. Rao actually just died at the age of 100 plus in India, great statistics expert and mathematician. And Fisher was also doing his works back in the 1920s. So this is not quantum theory, this is estimation theory. And the Fisher information has this terrible formula. But let me just share it with you. It's a sum of all possible histograms, all possible data, where you have the likelihood of the data. So this is a weighted mean of all the possible data, of the derivative of the likelihood of the data given theta with respect to theta. So if your data have a distribution which doesn't depend on theta, you can't learn theta from the measurement record. But if it has a strong dependence on the theta, then this will have a strong dependence. Then you get a large value of the Fisher information, and thereby you're also going to get a small error bar. We're not going to use that formula for anything. I just tell you that this is a formula that exists, and this is a kind of rigorous formula. And it suggests that then you should, extract this Fisher information, you should actually calculate the probability for all possible measurement records. And you should ask, how does that probability depend if I change the parameter just a little bit? And then you should evaluate this sum, which is of course infinite, if I could do hundreds or thousands of measurements here. So the good story is that we're not going to do that. We're going to use this concept of quantum trajectories, which allows us to actually extract all of this information on the fly, data point by data point, as they come into our detector. Okay, so the Fisher information, let me just say, for the binomial, it's all analytical, and the Fisher information has this value. It's the number of experiments over theta 1 minus theta. If the probability is 50%, you have the best sensitivity to changes, and it scales with n, which means the error bar is going to go as 1 over root n, like we know from normal sampling. Okay, so I already showed you this. I'm going to change, because I'm not going to look at preparing a state and measuring on it. I'm going to probe a system over time. So I'm not going to get re-prepared the same state over and over again. I'm going to be a little bit more less demanding on the experiment and saying we can actually use the same system and just continuously keep measuring on the same system. We can get a higher duty cycle of the experiment because it's continuous and runs all the time. So I'm transmitting light maybe through an atomic gas, and then I'm just measuring, for example, the intensity on the outside here. And then I'm going to get a time-dependent signal. And my question is now, that varying, fluctuating, time-dependent signal, does it play a role a little bit similar to what you see up here? What is the intensity I measure at different times? And this is something we have been studying a lot, and there's also been really great scientists both before me and at the same time as our group has been looking at that. But the idea is here that what do I actually learn from this noisy record? And in a standard experiment, you would say, well, maybe there's actually a mean value of that measured current who depends on the property you want to measure. If I'm exciting atoms with a certain strength, the mean fluorescence signal will depend on that strength. So that means you can back out that kind of results. But maybe you get even more out of analysis of the fluctuating signal. And I'll show you examples where we get out huge amount of information beyond what is hiding in the mean signal. But then that means we have to take into account an understanding of how this record is actually correlated and the noise is correlated over time. Now, there's funny when you look into the literature of sensing, and particularly this kind of continuous sensing, because there are two completely opposite paradigms where different groups say, we want to do back action evading measurement, meaning that I'm probing, but there should be no consequence for the observable I'm looking at. That's the school of Eugene Polsik, and actually also a little bit what they're doing in LIGO. And you can understand why, because I want to measure a certain quantity. And of course, I don't want my measurement to kill the state or turn it into something completely random. So if I keep measuring the same property and the state doesn't change, I just accumulate signal to noise. But then there's the opposite, and that is you say, I want as much to happen as possible, because then I kick the system, and then the system is going to undergo more quench dynamics. You're taking it away from steady state, and the way quantum systems evolve in time when they are not in eigenstates is actually much more significant, tells you much more about the Hamiltonian. than if you just look at a steady state. This is why in many branches of physics experimentally, you quench system and you look at the transponse of the system to quenches, because that tells you more about the Hamiltonian than just measuring a static property. So these are two different, completely opposite strategies, guiding principles, and hard to actually really combine. But we have a work now with a postdoc where we actually found a way to do both at the same time, which is kind of fun. Now, to tell you how a system evolves when I'm measuring it all the time, I'll bring us back in time to the work that we did with Jean and others were interested in 3-4 decades ago. You have a quantum system. Classically, I can control maybe a laser field or the way I'm interacting with the system. And there's going to be some measurement signal coming out to me standing with a detector, and that is going to be governed by the laws of quantum mechanics. This is a picture due to Wojciech Zurek on the interpretation of quantum mechanics, because there's a classical world in which my measurement apparatus sits, where my laser is sitting, and then there's this quantum description of what the atoms are actually doing. So this is the fence, the cut between the classical and the quantum world. Of course, there's only one world, according to Bohr, and that's the classical world, but there are phenomena, namely the ones over here, where we need the quantum formalism to explain what's going on. So it's a quantum formalism who solves the Schrödinger equation, but it's also the quantum formalism who gives you the probability for these outcomes. And it's also apparently the quantum who says that this is going to happen at random according to Bohr's rule. So we do the measurements on a single quantum system, and as you know already in the introduction to quantum physics, this causes a collapse of the wave function or back action or state reduction. These are different names for the same thing. And this time evolution is non-unitary. It's random, stochastic. It's non-linear because you get a projection and then you have to renormalize the state. And it's also non-local because it happens here, but the state is, of course, associated with a system sitting somewhere else. So this is the Einstein action at a distance that he thought was spooky. Bohr comments on this situation in a Como lecture in 1927, where he says that the measurement causes a complete rupture in the causal description of the dynamical behavior of the system. And I think that's a good name for what is happening. And in modern times with the quantum systems, there was in the 1980s mathematical work by Belavkin, Bakeli, and there was also more foundational work by Nicolas Gisin, more associated with relativity questions. But then in the early 90s, Howard Carmichael wrote a fantastic lecture note, Quantum Trajectories. Hegerfeld and Göttingen realized that you could describe some jump dynamics seen in ion traps, and with Dalibard and Castin, we worked out the thing that we thought at that time mostly as a method, a stochastic simulation method, simulating these detection events to serve actually a quite different purpose. Now, I will tell you how that works, and I'll tell it in our way, because, of course, that's the one that's closer to my heart. Imagine that you have a quantum system, an atom, which is in a superposition of a ground and excited state, and that the excited state is unstable and decay with a certain rate. What literally happens is that the field around the atom is also a quantum object. So as time progresses, this excited atom and zero photon component couples to become, with certain probability amplitudes, a ground state atom and a photon component who can travel in some directions. So this is quantum electrodynamics in a very simple model with a single excitation that goes from being in the atom to being in the field due to an interaction. And this is the picture of it. And what was normally done in quantum optics was to look only at the atomic state. So that means if I look at the atomic state, there's a population in the ground state, which is the incoherent sum of what you get from here and what you get from there. So this is this part and this part. There's an excited state population, which is also an incoherent sum, but there's only one term. And the coherence in the atom goes only from what you have on the left plus what you have on the right, which is zero here. And if you just sum this up, you get what we call a density matrix, because there's two different pure states, but they average into populations and coherences who solve a master equation that we were doing, and not we pioneered, but which existed, of course, already, and is a standard tool in quantum optics and quantum physics. Now, the approach that we suggested and that is being used here was to say, what if I don't put on sunglasses so I can actually see the photons? Then I would either, by seeing the photon, do a measurement, see no photon or see one photon. So the measurement, detection of light here forces the system to be either in the zero photon part or the one photon part, which means that with no click, there's no photon and your state is back into this superposition state, and this term is not there. Or if you get a click in your detector, you are in the ground state, and then the system will continue its evolution from there. So this replaces this master equation by stochastically simulating whether you should retain this part of the wave function or that part of the wave function. And that is something you will do at every single time step. So if you re-excite the atom, you can keep going forever, and you will have this little stochastically evolving wave function, which is always in agreement with this measurement process of seeing photons or not being emitted by the atom. And it was motivated in the article as a consistent derivation of this stochastic approach, because it is this Gedanken measurement who is actually driving the process. But now in modern times, these Gedanken measurements are the real measurements. We are actually sitting and doing measurements on signals coming out of quantum systems, and the quantum systems do evolve in a stochastic manner accordingly. It brings us beyond the normal projective measurements in the textbook, because we are not measuring on the atom, we are measuring on the light. And you can see the two alternative outcomes are not two orthogonal states. And that's because it's the photon field who is projected onto orthogonal states, the zero photon part or the one photon part. They're truly orthogonal, but the atom can be in states which are changing according to other laws. But we know what these laws are, we just derived them here. So the master equation can be simulated and averaged by just doing many of these, and that's how we thought this should be used in the beginning of this thing. But it is directly connected to the theory of more general measurements. So whenever you do measurements on a quantum system, textbooks, they are projective, so therefore there will be a certain possible eigenvalues coming out, and you have to act with projection operators, but more generally there will be an outcome and a corresponding operator acting on the system, which does not need to be a projection operator. In this case, 0 and 1 outcomes led not to projections, but to actually a step down in this case, and to a renormalization of the other component in that particular case here. So there's an M0 and an M1 operator in this form associated to this evolution and this evolution in this case. So I'm not going into details because this is not about the formalism of these trajectories, but I hope you get the feeling that, yes, you can do measurements which are maybe indirectly telling us about the system because I'm probing a field, not the atom, and there'll be a dynamics that we generally know. And there's also a Born rule, because the probabilities for these outcomes are, like for the projection postulate, they're now given by the trace of this operator expression. If you put projection operators here, you get exactly the population of these eigenstates, so as we normally see. Now we do sequences of measurements. And that gives us then what we call trajectories, because the state is going to evolve randomly in time in Hilbert space. So you have your Schrödinger wave function who is solving maybe a Hamiltonian part of the dynamics, but also has this measurement back action. And here's an example of a single two-level system who is doing excitation dynamics up and down due to a coupling, and then it jumps to the ground state every now and then at random times. And if you do it 100 times and you average, then you're going to get what we normally call damped Rabi oscillations. And in this case, it would maybe be more appropriate to call them dephased Rabi oscillations, because it's really because they jump at different times that they average out to give something more constant at the long times. And this is an experiment from here, Sergio Orr's group, where he's not measuring atoms, he's actually using atoms to measure a light field. And these atoms are going through this cavity, and they're picking up a phase shift due to the excitation, the number of photons in the cavity. And if there's no photon in the cavity, all the atoms tend to come out in the initial state. But if there's a photon, that phase puts them into an orthogonal state, and that is what is detected by these red bars. So this paper had a dramatic title, Watching the Birth and Death of Photons in a Cavity, because you're actually in real time tracking that there's 0 photon in the cavity, 1 photon in the cavity, 0 photon in the cavity here. If you average, or you do many of these trajectories, you will find that the average occupation of the 1 photon state is just what the Boltzmann distribution says. But of course, the Boltzmann distribution is the density matrix. It's the population, it's the probabilities in an average sense. But if you look, you're turning that into histories. And this is what trajectories are. Now, Serge did another experiment where he couldn't distinguish 0 and 1 because the phase shift was pi over 8 per photon. So the states were just rotated versions, but not orthogonal. But if you do sufficiently many atom detections, then they will come out in the original state every time, or 96% of the time, or 85% of the time, depending on the photon number in the cavity. So in this case, it takes much more atoms to find out what is the number of photons in the cavity. So here is 10,000 atoms. being injected into this cavity one after each other, and then you learn gradually that there's probably 5 photons in the cavity, and then there's probably 4, and then probably 3. What you're watching here is actually the slow decay of those photons out of the cavity down into the 0 photon state. So for no sensing, actually, I'm not sensing any classical unknown parameter, I'm just monitoring dynamics of a quantum system, but we are going to turn it into a sensor now, because if the system is subject to an unknown Hamiltonian, then it sits perhaps here as a parameter. And that means that the state evolves according to that Hamiltonian. So if you have a certain theta, you have a certain state, and then you also have a certain probability distribution that is conditioned on that parameter theta. And now comes the smart thing with this trajectory story, because I just look at one incremental next piece of information I get from the data record. And there's a certain probability for a certain value that depends on theta. So when I get that value, what happens to my estimation of theta? And this is called Bayes' rule. So Bayes' rule says that if you get more information, then you get an update of the original prior distribution for theta to be the one conditioned on the data, which is nothing but the prior multiplied by this factor, the Bohr rule factor that you get from up here. And this can be done sequentially. So I can, in every nanosecond or microsecond or millisecond, I can ask, what did I learn now? What did I learn now? What did I learn now? And then the same way as a wave function is changing by every measurement, this distribution also changes by every measurement. So it's a simple rule. It would be very difficult for me beforehand to say, given theta, what's the probability of the record? Because the record lives in an infinite dimensional space. But it's easy to take every data point and sequentially use it to update my knowledge about the system. So to give you a simple example, I have here a spin who rotates by an Larmor precession. I don't know the frequency, I want to estimate it. So after a little time t, it will have rotated by an angle omega t. And now, if I measure along that vertical direction, the probability to measure the same direction again will be cosine squared omega t. And here, I have a record where I measure the same direction, same direction, same direction, then I measure the opposite one for some time, and then this is what the record does, and here what the arrow shows is indicating what are these time-evolving probabilities between these different measurements. But I want to back out what was actually omega given the detection results. So we can assume so here I measure spin up, 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 down, 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 so that's the data sequence that I'm looking at, and let's assume 3 different values of the Rabi frequency. The Larmor precession frequency, sorry, omega 0, half of it, and 3 half of it. So I start with 1/3 probability assigned to each of them, just a uniform prior, and then if I don't see rotations, I stay in the up state, that will actually favor a small value of the Rabi frequency, because that's in agreement with not rotating, while the high one is suppressed in Bayesian update probability. So you see how these 3 probabilities change according to every single measurement, and you can also understand why they change this way. Now there was finally a click, so maybe the lowest one was not the more likely one. Immediately it drops down, the other one comes up a little bit more, and then after 10, 20 measurements, I'm actually getting more and more convinced that it's the middle value, which is the one I assumed in this calculation. So this is how we can do the Bayesian update using the measurement trajectory in this particular case. Here we do continuous, not continuous probing. Here we're doing the probing where we do it at relatively long intervals, and then what you see is there can be an aliasing problem, because I don't know if it did 1 cycle or 2 cycles between the measurement or 3 cycles. So there are actually a number of frequencies that are compatible with the same data set. If I choose a better timing, then there's only 1 coming out, and if I measure much more frequently, I actually get a suppression of my learning rate because I get a Zeno mechanism that suppresses the dynamics. So there's some design choice here. You don't want to measure all the time and prevent the dynamics from happening, and you don't want to measure too rarely because you don't want this to happen, and you also want to have a decent data rate coming in, of course, in your measurement. So this is a super nice principle, and let me just show the 2-level atom of before. I drive it with a laser field, and I got this condition dynamics. This is a solution of the trajectory stuff, but in this map here, there's 20 photon quantum jumps. There's 20 photon detection events. And I would say, if you tell me there are 20 events in a certain amount of time, can you tell me what is the Rabi frequency? Well, you would say 20 events. This is actually the excitation probability as function of the Rabi frequency of that system. And 1020, that's around this thing, but the error bar is probably plus minus the square root of 10 or 20. So can I see what is the Rabi frequency if the signal has that value with an expected error bar? Sure not, because all these values are compatible with that data point. But here's the simulation. So this is what it actually looks like. I assign prior values for everything between 1 and 7 times the decay rate of the atom. And you can see very quickly, I know what is the Rabi frequency with almost zero uncertainty, or not zero uncertainty, but with a very small uncertainty. And you can ask, why did that happen? Well, that happened because it's not the number of counts that matters. It's actually the random durations between the counts that matter. Because that distribution is showed also in this transient behavior here. There's a rapid oscillation because after every click, the atoms is put in the ground state and it starts oscillating up and down. And there's a little clock there, which is exactly the Rabi frequency. In the long time, it's damped out and you have you lose the phase. But for the short times, you have a phase of that clock. And the next click, if that happens within that time window, you can also determine that frequency. And that's exactly what happens here all by itself. So that shows the power of the measurement back action, what I call the quench dynamics here, because the measurements themselves make the system more sensitive for the subsequent measurements to occur. Here we do homodyne detection. So this is probing the field quadrature instead of measuring the number of photons. And here we have a similar story. And funnily enough, it actually has the same sensitivity if you want to measure a Rabi frequency on resonance. But you have to use the right phase of that local oscillator, because there's also another component, the imaginary part, or the phi-O2 out of phase of the field, which tells you very slowly what is the Rabi drive. And the reason is that you're spinning around your block vector in the xz plane, so you want to measure the x or the z coordinate, but if you measure the y coordinate, there's not much information on that other property of the system. So we can analyze, as I said in the beginning, we can analyze a scheme, and then we can hope it's a smart scheme. And this is, of course, something we're also thinking about. Now, the Fisher information. I started telling you that there's a Fisher information associated with the data. That's very difficult to calculate, because the data is the entire data record. If I want to tell how good is this on average, if I measure for 100 milliseconds, then this looks almost impossible to do. Sometimes it can be done easier. For example, if you just have the data record accumulated in these jump times, they're actually all pulled with the same probability distribution because you reset into the same state every time. So that's a question of matching actually just the time intervals to that waiting time distribution. But some other cases, this will be very complicated. But we found a way, and it's in this paper because it's still a complicated way, but you can actually sample that one by doing many Monte Carlo trajectories. That will sample typical records with the right probability, and then you can see how much does this quantity actually perturbatively change if you modify the parameter a little bit. So this is a method that can be applied, and so that is fine. And we actually calculate analytically, for what I just showed you, that the classical Fisher information does not depend at all on the Rabi frequency. Despite saturation and everything, you are equally good at distinguishing between 1000 gamma and 1000.1 gamma as you are between 0 and 0.1 gamma if you do photon counting. And that's actually quite remarkable. And the story is, of course, that we are looking at this waiting time distribution and are matching the waiting times to the red curve, and that matching can be done no matter how big is the Rabi frequency, equally well. And if I do okay, so this is how the calculation was done. And if I do the homodyne, we actually find the same Fisher information numerically from our studies. And just this year, Igor Lisanovsky in Tübingen wrote a paper from which I could actually understand why these two give the same thing, which is very nice. So there's a lot of interest in actually analyzing this conditional dynamics. I'll maybe just make one comment. Homodyne detection is measuring the amplitude of the field. If you Fourier transform that, you get the spectrum of the field. The spectrum of the field under strong driving shows something called the Mollo triplet. And the Mollo triplet has peaks which are separated by the Rabi frequency. So that means the fluorescent spectrum does tell you what is the Rabi frequency despite saturation, because the peaks are moving out. But if you look at the spectrum alone, it only looks at 2-time correlations in the signal, and it actually does not get near the total thing here. So there's a lot of higher order correlations because all these small perturbations of the system by homodyne detection is only kicking the system a little bit, and therefore there will be 4-order, 5-order, 8-order, 10-order correlators. And of course, this is almost impossible to catch, and that's why it's so much nicer to use the trajectory and just pick it up as it comes in as data instead of trying to calculate it. Now, here's a thing I'm very proud of sharing with you. This is a crazy story. This is something called the quantum Fisher information, which is different from the classical Fisher information. The Fisher information I talked about tells how much does the classical data tell you about the classical parameter. Okay, so it's a quantum machine who does it, but the data is numbers in my computer, and how can I learn from those numbers what is the parameter I'm looking at? The quantum Fisher information says what is the best measurement you could ever do by any measurement on the system. And that in some sense relates to how different are the states, the quantum states corresponding to the different situations. And the state I'm talking about is actually the state of the emitter atom and the entire field that has been emitted all the time. So if I don't detect it, then for 1 second I'm going to create a light beam from here to the moon containing 1 billion photons or more, and then that quantum state of all these photons, that's the quantum state who tells me what was the parameter. If I can have 2 different values of the Hamiltonian, there might be 2 different quantum states, and it's the overlap between those 2 quantum states who tells if I can theoretically distinguish those 2 hypotheses from each other. The same as in a small quantum system. Here looks, of course, impossible because nobody can calculate these quantum states, so how can we calculate their overlap? And the good news is that on a good Sunday afternoon, we actually found out that this is easy to do. It's even much easier to do than the classical Fisher information. So I will tell you that there's a formula. You have to take the trace of a density matrix, and the density matrix solves this crazy equation where it looks like a normal master equation, but the density matrix is acted on the left by the one hypothesis, and it's acted on the right by the other hypothesis. Okay. And the way we got to this one was to say, let's take a little quantum bit. We borrow it from one of our quantum computer friends who controls whether it's this Hamiltonian or that Hamiltonian who applies. And then what is lack of overlap between those 2 states is what our computer friends call decoherence of the qubit, because that's what makes it distinguishable whether you were in one or the other state of the qubit. So it's actually a single qubit observable, and that single qubit observable is just part of this joint density matrix of the qubit and the emitter system here. So there's a very simple formula to calculate that thing. So that's a kind of result we're playing with also. And this sets the benchmark and also the challenge to our experimentalist friends. Now you go and you find the good measurement who actually reaches that one. So we calculated it, and for the 2-level system, it's 4T over gamma, which is exactly the same we got from the counting and what we got from the homodyne detection. So we know they actually saturate the best you could ever do. And it's kind of surprising because the correlations in the field could be non-local or anything, but you're actually allowed to sit sequentially and just measure the signal as it's coming out, and that will give you all the information that you need to estimate these parameters. It's not true if the transition is detuned, because then counting doesn't tell you about the phase on that detuning. There's elements of the dynamics that you don't capture right. But with a very smart postdoc, we're actually now making the setup who can even exhaust the quantum Fisher also in those cases. So this is really active research now, not by us only, but by really quite a few groups who are obsessed maybe by the same problem. How can we actually extract this information as good as possible? So one really talented Chinese postdoc working with Martin Plenio, but now being back in China, Yu Yang, has done fantastic work in this. Igor Lesanovsky's group in Tübingen, Marco Giannoni's group in Milan, and then works that we're also doing in Copenhagen, is trying to push this even further. What is next? Well, what is next is putting up funny strategies, something called encoder-decoder ideas, negative masses, doubling the system degrees of freedom, which we're also looking at, or having ancillary degrees of degreedom that could act as a memory for the dynamics of the system, and now finding out which measurement protocol. And no matter what of these things you have in mind, the best idea, you can go back and do this quantum analysis or classical analysis just to see how it works. And I think that's very nice. Sensing with many body systems, near criticality. Sure, there will be extra sensitivity. Well, how do you sense them? By continuous probing. Then you would also like to employ this particular method of analysis. So that's really what we're looking at. I'd like to finish. I'm speaking a little bit over time, but I promise I will not speak for the next 15 minutes, also not for the next 10. What if the parameter you want to sense is time-dependent? I mean, I talked about a constant thing that I want to sense, but very often, for example, the heart diagnostics, that's of course a time-dependent signal. So you want to track something that evolves in time. And this is something that of course, is also very important. And we have been looking into that also. So we have this Bayes rule, and I like to think of it in the following way, that I have an unknown parameter theta, And when I do my measurements, there's a shrinking of the probability for that distribution because I learned something, right? But then if it changes with time, there will also be a spreading of that distribution because it may have different values in the next time step. So if theta is, for example, given by a Brownian motion or Ornstein-Uhlenbeck, a known statistical noise process, a hidden Markov model to be more general, then I can at the same time take into account how I learned something about it and how it spreads towards the next time step. So we have made this kind of theory where we have a joint classical dynamically evolving probability distribution together with a quantum system who does the measurement on the system. And that actually works very well, and these are just some examples of how that spreading may be modeled. I need to have a prior for the spreading mechanism to use Bayes' rule. So this is, again, the Bayes' rule story, and I just like to share with you how I think about it. I like to think about it as if the classical quantity is a quantum property. It's just in a diagonal state. So it's actually the same as a classical probability distribution. But this is a hybrid formalism which is actually compatible with a full quantum formalism. So you can think about your density matrix as being a density matrix for your system degrees of freedom, which is the normal case, and of the unknown classical parameter. And in that way, a full quantum formalism and the master equation is actually just running and giving you the conditional state. And the quantum trajectory in this language is automatically being a trajectory for the probability distribution on the unknown parameter. So just pretend that the magnetic field was a quantum degree of freedom. I have to assume it's one that doesn't evolve or one that doesn't have too many quantum properties, but that can be fixed by which Hamiltonian I pick for it, for example. So here's an example of such a fluctuating magnetic field, and it's fluctuating. The true fluctuation modeled here for the experiment is the red curve, and the green curve is the maximum likelihood, so that's the peak value of our conditional probability, and the yellow area is the kind of uncertainty. And this is an atomic magnetometer, gas of atoms, where we are probing by optical interrogation, and the true field is the green curve, and this blue thing here is the error bar and also the most likely value we are estimating. So you see, I'm happy. I'm also a little bit unhappy because it seems that I'm not really getting the fast evolution because they're very surprising, and I have to accumulate data before I actually accept that there was this drop. So I'm always getting a little bit late on this evolution. And then that led to the last thing I want to say about trajectories, namely a question I asked myself from the early days of the trajectory story, but I couldn't find a good answer. Namely, you do your measurement record, you have a conditional state according to the formalism I just described, but do the later measurement not also tell us something about what the state was earlier? Okay. Because if I have a system who is in a certain state, I'm accumulating more information also by the subsequent measurement, also about what the state was earlier. Of course, all our friends in archaeology, I think you can go out and see an archaeology exhibition, that's what they do all the time, because they make a discovery now, but of course they infer something about the past. So this is quantum archaeology. So how do we actually do that? If I monitor a quantum system, do the later measurement also inform me a little bit better about what the state was at the earlier time? And I couldn't find a way. Just, is there a better row? Is there a better psi due to later measurement? But actually, that's the wrong question to ask. The right question to ask is, what are my predictions for the outcome of an unknown measurement taking place at that time? Can I make a better prediction for such a measurement? It becomes a little bit more normal quantum mechanics. So we actually use that to generate the way to make this kind of retrodiction now a decade ago. So let me just share with you the first application of that. So here's the graph I already showed you from Serge Roche group, where we have the inferred probability for the photon number in the cavity. That's for the measurement of the photon number. What's the probability to get 5, 4, 3, 2, 1? And this is what you see. We got the exact same atomic data, and then we used this theory, and then we got these curves. Okay. So it's exactly true that along this patch here where you think that there's 2 photons in the cavity, the later measurements actually also tell you what was the value, and it confirms there was actually 2 with a higher probability than you thought, because next measurements confirmed the value 2. So that's why we have this much closer to unity, and the spike was clearly just because you measured the wrong statistics of the atoms, but everything is possible. I can throw a coin 5 times and get heads every time. It doesn't mean it became an unfair coin. It's just statistics. So this is what happened here. So this is just for the quantum state. Now we do the same to the sensing. So here this is what it looks like if I go backwards and forwards, and you don't see the big difference, but it's about a factor 2 smaller error bar, and some of the spike evolutions actually captured much better. And you see it better in this case, because the orange curve with the fatness here has a smaller error bar, and now there's no surprise, and you're not getting late, because the later data, of course, it retrodicts that there was something happening in the past, and this is now folded in. So this has been done in collaboration now with an experimental group in Shanghai, Yan-Hong Xiao, who has demonstrated that this actually works. There's a lot of other things going on here. There's also squeezing going on due to the measurements and these things, but I mean, I did not want to talk so much about that, but talk more about this inference problem, but it does benefit from some of these other mechanisms, which are clearly here. So this is her experiment, but it's too late now. So I want to finish here and then ask me about what is in this graph, if you want to know what it is. The last thing I want to say is that the sensing of time-dependent signals needs this prior model. So we can do that if I have a prior idea about what kind of noise process is this guy doing, then Bayes' rule works. What if I don't have such a rule? Well, what we did with Yan-Hong in this experiment was that we tried many models with this known field where I could predict the outcome, and then we trained a neural network. And we saw that the neural network was as good as me. Okay, I think that's a daily experience for many of us, that sometimes it's even better than us. But then after having trained it on a place where I could benchmark it because my theory worked, then we make the noise crazy. And then we train it on crazy noise. And then we trust that it might actually be good. So here's the neural network design, and here is the real signal that she exposed to atoms. That's a real fluctuating magnetic field. And the orange curve is the one inferred by the deep learning, by the recurrent neural network. And it's very much on top of each other. And I would not have any chance to actually make that prediction here, because the stochastic model is a crazy one that I cannot put into my theory. So like in every other field of sciences, this is a field where AI may also come to our help. I think it's informed, right? It's expert users of a technology like AI here, and we can always go in and benchmark it in corners if we are kind of conservative. We don't like the idea, but I definitely think there are many unknowns in many experiments, which you will of course also gloss over if you just train the experiment the way we did here. Last slide. Conclusion. The state of a quantum system is conditioned on probing outcome, and it follows a quantum trajectory when monitored continuously. And if you do that, there will be this stochastic random changes of the state, and there will be a transient response after that. There will not be steady state, there will be evolution, which is triggered by the measurement. And in metrology and hypothesis testing, exactly these transients are the ones that will give you signatures in the signal that might be much stronger. So it's actually important and also very useful, but it's also feasible to use this Bayes rule to get this out. There is a golden standard, the quantum Fisher information, so we can actually benchmark whether we reach that or not in many cases. And then, of course, this Bayesian analysis works if at least your signal is of a kind of model you can model. Otherwise, turn to AI. Thank you for your attention.